In this video, we're going to discuss how the small signal diode works. So in your kit, you can find this strip of small signal diodes. They're glass, they're mostly red, and there's a little black line on them. So what is a diode? So far we've used LEDs. Those are a special kind of diode. They emit light. But this kind of diode we'll think of as a one-way valve for current. So how do we draw them? The circuit schematic for the diode is an arrow with a line at the end. And if this was an LED, we'd have some little lines coming out. That would be the light coming out of the diode. But here we're just talking about a diode that does not emit light. And the purpose is to block current. So current will only go in the direction of the arrow. So that means if we try to make this point voltage bigger than this point, the current should not flow in the opposite direction of this arrow. Current should only be able to flow from this voltage, from this point to this point. When we look at our physical diodes, how do they line up with this schematic? The black line on the side of these little red diodes lines up with this line. So if you're looking at your diode and you see there's a black line on it, that line matches up with this line. So when you're building, you have to make sure you put these in the right direction, otherwise the current will go the wrong way. So what does it mean to be a one-way valve for current? Let's think about a curve where as we apply a voltage to one side, so let's say we ground to this side of the diode and then we apply a voltage to this side, what we would hope to do if we were a perfect one-way valve is that as we try to increase the voltage, how much current can go through the diode? Well, as soon as the voltage is just a little bit positive, we should get infinite current. And if we try to apply a negative voltage, we should get zero current. So that would be the ideal case. An ideal current would block all, an ideal diode would block all current when the voltage is negative and let infinite current through as if it were just a wire when the voltage is even just a little bit positive. Now, a real diode, unfortunately, is not that efficient. It takes a little bit of voltage to be able to kind of open the floodgates to let that current flow. So if you want to use the analog to a mechanical system here, you could think of current as water flowing through a pipe, and the diode is a mechanism that if the water flows in one direction, it pushes open like the spring-loaded one-way valve. And if the water tries to flow in the other direction, the valve closes because it doesn't let water flow. So like here's our pipe, and we've got these like V-shaped channels, and there's a spring that tries to close that channel. And if water flows in this direction, it opens up and flows through. But if water tries to flow in this direction, it closes. And the penalty for having that little spring there that keeps this closed normally is that it takes a little bit of water pressure to be able to open up that floodgate. So the same idea here for the diode. We need a little bit of voltage here before any current will flow. So a more realistic model for our diode is that no current will flow until we hit some like magic voltage. And that magic voltage is usually 0.6 volts. So we'll call this the approximate what happens with a diode. So now we can say as long as we have at least 0.6 volts across the diode, current will flow and an infinite amount of current should flow. And you could probably guess that in reality something in between happens, so a real curve looks more like that. And so this is the what the real diode does. So as you start putting a little bit of voltage across the diode, a little bit of current will flow until suddenly on this exponential scale, eventually you can't put any more voltage across it because there would just be huge amounts of currents flowing through. Now, if you were an LED, this magic number would be more like 1.8 volts. But that's actually varies with the color of the LED. So, and I forget what, but from yellow to green to red to blue is an increasing amount. So by the time you get to a blue LED, this is approaching 2.5 volts, and then a nice high quality white LED might even be more than 3.3 volts. So something to remember as the kind of the quality or intensity of the LED goes up, that voltage usually goes up too. So what are we going to do with this small signal diode? Why would we want a one-way valve for current? Let's draw a circuit. We'll have a V in go to the diode, and then we'll give our current someplace to go for now, like maybe like a 1K resistor. And here's our V out. And let's pretend that our input voltage versus time is a sine wave. Why not? So we've got some signal coming from some source, and let's pretend that it goes pretty big. Let's say that this is like a 3 volt peak, so 6 volt peak to peak sine wave. So if that is V in, what would happen to V out? Well, let's do the ideal case. The ideal case would, if the voltage is at least positive, current would flow and we get some voltage out. And if the voltage is negative, no current would flow. So if no current is flowing this way, then there's no current through this 1K resistor, so there's no voltage across it. So if one side is ground, the other side must be ground when this voltage is negative. So that means in the ideal case, the output voltage would match when it's positive and be 0 when it's negative. So that's the ideal output. And then if we wanted to say something like, well, on a real LED, we've got this magic 0.6 volts here. That means that the output voltage will be 0 until the input hits 0.6, and then we get a matching amount of, like the matching shape. And then when it crosses 0.6 again, it goes back to 0. So there's kind of this, we call it like a loss from the ideal would go all the way to 3, the non-ideal would go to 3 minus 0.6. So we kind of lose 0.6 volts by trying to use this circuit to make V out always positive. But it's not taking the absolute value. It's not turning the negative side positive. It's just throwing away the negative voltage. So eventually we'll probably come up with a circuit that doesn't throw that away, that actually does take the absolute value, so that we don't lose that signal. We just want to make it positive. But we'll do that later. So this is probably the most common use for a diode. Let's talk about another interesting case, though. In this case, the temperature dependence. So this is true for all of our electrical components. As you change the temperature, what they do probably changes too. So the value of the resistance of a resistor depends on temperature, but not by very much. So the same idea here for our diode. We've got a voltage versus current curve, and it kind of looks like that, where this is the magic 0.6 volts. This is usually given at room temperature, something like 25 degrees Celsius. If I were to warm up the diode, the shape of the curve shifts to the left. So this is increasing temperature. So if we maintained a constant amount of current through the diode, and we were to warm up the diode, the voltage would be maybe 5.9 instead of 0.6 now. And that would be, going from maybe 25 degrees C to 30 degrees C. So it's a pretty small change. But what this means is that we can make a temperature sensor out of this diode. But it's a relative amount of temperature sensor because we're probably not going to calibrate exactly what this voltage means. So how do we make a relative temperature sensor? Well, we would have two diodes. So I'm going to have 5 volts go to a resistor to a diode to ground. And maybe I'll choose a 1K resistor to set the current in something around the milliamps. And here would be my kind of like V sensor, the voltage output from this circuit. And it should be about 0.6 volts. But if I were to touch it and warm it up, it would go down to 0.59 volts. what I can do is I can compare that to another of the exact same circuit, going to ground. So we've got another 1K resistor. We should have the exact same current flowing through this diode and this diode because they're the same. And I'd call this the reference voltage, which would also be something like 0.6 volts. But I won't touch that one. I'm only going to touch this one. And so this one will keep its value of 0.6 volts, and this one will go from 0.6 to 0.59. So if I compare those two voltages, and I'll put them into my multimeter, so that V with a circle there, this represents my multimeter in voltage mode. What I would see is that at the same temperature, these two voltages should be equal, so the multimeter should read 0. And then if this is the black side and this is the red side, as I touch this one and this voltage goes down, my multimeter should go up by 0.01 volts. Then what you can imagine is we could take that difference in voltage and we can magnify it with an op-amp circuit and turn it into something that is more visible. So we don't want something that changes by 0.01 volts. We want something that changes by like 1 or 2 volts. So how would you do that? You've got Vref, and you would do minus V sensor, and maybe you would multiply that by a factor of 100, because 0.01 volts times 100 would be like a change of 1 volt, and we want that to be V out. So now, looking at this equation, you would then say I would use a differential op-amp circuit, and I would take this as one input and this as the other input, and I would choose the resistors to get a gain of 100. And now I've got a temperature sensor where if I touch one, the voltage goes up, and maybe if I touch the other one, actually this one would go, the overall voltage would go down. So I can actually make a voltage go positive and negative depending on which one I'm touching. So that's pretty neat. I don't want to build that circuit and give it away, but let's look at what happens when we try to build something with our diodes. So I'm just going to take 2 of my diodes out and get them into my breadboard. Now the thing about these diodes is these diodes are not resistors, right? A resistor is something whose voltage versus current curve is linear, right? With, in this case, the slope of 1 over R, which instead of resistance we would call conductance. So when a device does not have a linear shape to this curve, it is no longer a resistor. So a diode, we can't put with our multimeter and measure its resistance. It doesn't have a resistance, it's a diode. Instead, what we do is we have what we call the forward voltage. So this magic 0.6 volts, we call the VFWD. The forward voltage of a diode is roughly 0.6. And of course, now we know that it's not really 0.6. It has a shape that depends on current. Okay, so there's one diode plugged in, and I'm going to do another diode right next to it. And according to my circuit, I want 2 1K resistors attached to 5 volts. Okay, and then I want my diodes to end up in ground. And as soon as I connect them to ground, current will flow. So now current in this top diode is flowing from 5 volts through the resistor, through the diode to ground. And I'll do the same with this one. So now theoretically, these both at this point and this point are 0.6 volts, and they have the same amount of current going through them because we could calculate what's the voltage across the resistor. We have 5 volts total, 5 volts minus the 0.6, we have 4.4 volts across the resistor. 4.4 volts divided by 1K should be 4.4 milliamps-ish. Now I'm going to take my multimeter. And what do I expect? I expect 0.6 volts across the diode. So I'm going to put the black lead on the negative side and the red lead on the positive side. Okay, and this one I get like 0.66. And this one I get 0.66. Okay, they came off the same piece of tape. They probably came out of the factory at the exact same moment. So they should be pretty identical. I'm on the 20 volt setting here, so I can get more sensitive by going to the 2 volt, which is the voltage I'm reading is 0.6, is still less than 2. So now I get another decimal point. So it's more like 0.691. 0.691. I'm gonna just gonna take my fingers. I'm gonna rub them together, make them warm. And the goal here is I'm gonna touch this to try to warm it up and see if the voltage goes down. But I don't want to really touch the wires coming out, the legs, because I might add myself as a resistor in parallel and let some current cheat. So really, I'm trying to warm up my fingers, and I'm trying to get my hot skin on the glass of the diode, but I'm not trying to like short anything. So I'm just trying to warm up that diode. So warm, warm, warm. And I'll quickly go and try to measure it. Now it's at 0.684. Now we can see it as it cools down. The voltage goes back up. So one of them stayed at 0.69, and the other had dipped down to 0.68 something, and now it's back to the original temperature. So it's kind of hard to see what that voltage was, and the change wasn't very big. So what I'm going to do is I want to see the voltage instead from the one I'm not touching to the one I am touching. And there's 0 volts difference between the two. And I will even make my multimeter more sensitive. I'll go to the 200 millivolt setting. So now I'm reading millivolts instead of volts. So the difference from one diode to the other is less than 1 millivolt. And if I just touch this bottom one, I'm warming it up with my finger, and we could see that the difference, and that one's decreasing, and I've got the red one on it, so the voltage difference is becoming larger, and we got a difference of almost 11 millivolts as I warm it. And of course I could touch the other one instead. Now the voltage will go positive as the one that I was originally touching cools back down, and the one that I am touching warms up. And that's all based on temperature. Now, how can I build a temperature sensor out of the diode? But the signal is too small. So if I say that my signal goes from, what was it? It was 0.68 when it's cool to 0.69 when it's hot. So it's changing by 0.01 volts. I want to multiply that by a factor of 100 so that I can see a 1 volt change. We prefer to see big voltage changes, not small ones. So I could take that signal, and what would I do? I could say try to put it into a times 100 op amp. The problem is when I multiply this by 100, now my signal is going to be 68 volts that changes to 69 volts as I warm it up. And my oscilloscope can't see voltages bigger than 5. So I need to subtract 0.68 volts from the signal. Then I need to multiply by 100 so that my signal is really going to be 0 going to 0.01, because first I'm subtracting off 0.68. Then I multiply by 100, and then I see a voltage of 0 to 1 change. So I can't just take one diode and put it directly into an op-amp circuit. I need to use 2 diodes, one that has the exact voltage of 0.68, so I can subtract it off. I don't want to try to make 0.68 with a voltage divider. That's why I'm going to use another diode. So when we look at this one, here's one that's making 0.6 for me, and here's the one that's changing. I'm going to take this, subtract that, and then multiply by 100 or something. Okay, one more caveat. When you look at these two guys, they might not have come from the same factory at the same time. Same thing with the resistors. Maybe these two are the same, but these two are not. And so this might be a 1K, but this might be a 1.1K, which means that they don't have the same current going through them. So even if they're the same temperature, they might not have the same voltage. So it could be a little risky to just use 2 fixed resistors here. So I'm going to do something just a little tricky. And this is more complicated probably than it needs to be. But instead of having 2 real resistors, that one could be 1K and one might be 1.1K, I want to try to do something where I want to fix it. So I want them both to have the same voltage, but one might need to have 1.1K and one might need to have 0.99K. So I need a variable resistor somewhere. So I'm going to take my potentiometer and hook it up in this super strange way where the middle tap of the potentiometer, which is usually we think of the output, is going to be the input of 5 volts. And the sides of the potentiometer, which are usually where we put like 5 volts in ground or 5 volts in -5, those will be resistors that go to the diodes. So if I set the potentiometer to the middle, and this is a 10K pot, that means from here to here should be like 5K, and from here to here should be 5K, and hopefully those voltages are equal. So if we take this and put it to our multimeter, we would expect to see 0 volts there. But if we didn't, even if they were at the same temperature, we would know that maybe each diode is a little different or the pot's not in the middle. So now what we could do is we could turn the knob to make that number go to 0, so that maybe this needs to be 4.9K and this needs to be 5.1K to make those two the same voltage at the same temperature. So remember that the potentiometer has 3 wires and it's got the knob on it. So that means that the middle one is going to be 5 volts and the outer ones will be the diodes going to ground. This is, of course, is not something you'd ever want to draw and submit. This is just to remind you how the potentiometer in your kit works. This is the correct circuit diagram. Okay, so let's build that. It turned out that my 2 diodes with 1K resistors worked pretty well, but let's pretend that they don't work so well. So I'm going to find my potentiometer, and it's got 3 legs. Hard to see on the video, but the middle one is going to be in a row by itself. The outer ones are going to the resistors, to the diodes to ground. And then I will apply 5 volts to the center tap of my potentiometer. And if I'm in the middle, I can use my multimeter on this very sensitive voltage scale to look at the voltage from the side to the side. And what I would like to do is turn the knob until it gets to 0. Might take a few hands. And it's going to be pretty sensitive, so don't kill yourself trying to get it exactly at 0. And another thing to notice is if I turn the potentiometer too far to one side, what happens? This one's getting like a 10K resistor. This one's resistance is going to 0. So if I eventually turn it all the way to 0 on that side, the end scope turns the power supply off, because when there's no resistor in series with one of these diodes and I put 5 volts across it, how much current should be going through the diode? It should be an infinite amount of current. So we're using this as a current limiting potentiometer here. So basically the angle of the pot should be somewhere in the middle. If you're turning it all the way to one side or all the way to the other, something's probably wrong. Okay, the last thing. Why is this called a small signal diode? Well, the heat dissipated by this diode is the voltage across it times the current through it. Well, if there's current going through it, it has 0.6 volts across it, and then we could just figure out how much current is going through the rest of our circuit. These are something like 0.1 watt diodes. So they're not really meant to be dissipating lots of heat. These are kind of blocking small amounts of current from going backwards. There are lots of other types of diodes. There are Shocky Diodes, which are designed to have a lower forward voltage so that you don't lose so much voltage across. And they can come in very big sizes, like physically large, so that means they can dissipate more heat. So depending on what you're doing, you can find diodes of all shapes and sizes, just like you could find resistors and every other component in lots of different sizes.